Hi, in this video I will present our work on deep geometry-aware camera self-calibration from video. This is joint work with Moritz Knorr and Christoph Stiller, and my name is Annika Hagemann. The goal of this project is to accurately infer the intrinsics of a camera. And as shown in these images here, the intrinsics characterize how a camera projects points from the three-dimensional world to a two-dimensional image, and they are an important precondition for tasks such as visual SLAM, structure for motion, or neural radiance fields. In general, camera intrinsics are obtained during calibration, and here one distinguishes between target-based calibration and self-calibration. While target-based calibration can yield highly accurate calibration results, it is quite time-consuming and not always feasible. Self-calibration, on the other hand, can be applied during application, but since it cannot rely on prior knowledge about the environment, it is a much more challenging task. Now, before we go into our approach to self-calibration, let's briefly recap the state of the art. The classical approach uses a structure for motion system and refines the intrinsics together with poses and depth during reconstruction. However, classical structure for motion suffers from failed reconstructions due to lack of texture, outliers, or too little camera motion. More recently, deep learning approaches have been proposed that either regress the intrinsics given a pair of images or learn the intrinsics of the training data. However, to be applicable to different cameras, they require training data from many different cameras, and they omit the prior knowledge about the underlying multi-view geometry. We argue that self-calibration should exploit both the capabilities of deep neural networks and our prior knowledge about the underlying multi-view geometry. Given a pair of images with overlapping field of view, our model predicts dense correspondences as well as confidence weights. They are then passed through what we call the self-calibrating bundle adjustment layer, which uses a differentiable variant of classical bundle adjustment to estimate the intrinsics together with relative camera pose and depth. The model is trained end-to-end such that it learns to find correspondences and confidence weights that are most suited for self-calibration. Overall, we thereby exploit the capabilities of deep neural networks while keeping the classical bundle adjustment, which enables generalization across camera models and cameras. Having seen the general idea, let's now look into the detailed architecture, and here we build upon the deep visual SLAM system DroidSLAM. We assume an initial guess for poses, depth, and intrinsics to be given, and in the first step, features are extracted from all images. Then, based on the feature maps, a correlation volume is computed, which contains the correlations of all pairs of pixels in the two feature maps. Now, a gated recurrent unit updates the current estimates of correspondences and confidence weights and passes them to the self-calibrating bundle adjustment layer, where intrinsics, poses, and depth are updated. These operations are repeated for a fixed number of iterations until the final self-calibration result is obtained. Now let's look at some results. Here's an exemplary video from the Tartan Air dataset, and at the top you can see the ground truth intrinsics and below the current estimate. And you can see that after a short warm-up, the estimate quickly converges to the ground truth. We evaluated the calibration accuracy across 4 different datasets, including images with distortion. And we found that the proposed approach yields state-of-the-art calibration accuracy across all of these datasets. The proposed self-calibration enables performing 3D perception tasks with unknown cameras, as shown for the example of trajectory estimation and 3D reconstruction of YouTube videos. Our code is available on GitHub. Thank you very much for your attention.